Good morning, officially. All right, so last day, I'm gonna keep that for just in a little bit here. Last day we started with functions. So as a quick review, we started talking about functions. We had function notation, f of x. Function notation, we started talking about that and we said, well, we've been dealing with expressions and equations already, so functions are just kind of a fancy way to denote those. We talked about what is a function, right? One input can only give one output, that is a function. And then we talked about the net change, which is going to come up again today, f of b minus f of a. The function evaluated at point B minus the function evaluated at point A, assuming that point A is less than point B, right? So kind of the second output minus the first output, that's the net change. We talked about the domain and range. Domain is all the possible inputs, kind of shorthand here. The range, the possible outputs, right? And we've seen domain before. We haven't really talked about range, but we looked at some graphs and we figured out what the domain and the range are. Let's scoot this down a little bit more. Then we talked about general shapes of graphs, right? So some of the ones that we need to recognize, well, a straight line, so a linear equation would have this kind of straight line situation. If we've got an even power as our highest power, we've got this kind of parabola shape, right? If we have an odd power, then we have this kind of dance move shape, right? For the root functions, right, they're kind of the same, but on an angle. And then we also talked about the reciprocal functions and the absolute value functions. But I said the first three in that graph, now where do I have? We're in this table, right? These first three, as long as you've got a good handle on what these look like in general, then we can deal with these as they come up, right? But these, I want you to have a really good handle on, you know, what do you expect when you see something that has the form x to the power of n, right? And then even or odd power. So the shapes of common graphs, or common functions, I should say. All right, so recognizing those. And what else did we talk about? Oh yeah, we used the vertical line test. Man, we did a lot. Scoot this down even more. We used the vertical line test to determine if a graph represents a function. To determine if a graph represents a function. So here, right, if you're asked, okay, is this a function? Well, we said in the definition, right, we can only have, so each input can only give us one output, right? Graphically, what that looks like is if you take an imaginary vertical line at every point on the graph, each value of x, right, so each kind of vertical point can only cross the graph once, right? And so that's the vertical line test, but it's really just applying the definition of a function. So, and then we had a look at some graphs and decided if they were functions or not. And then we talked about solving equations and inequalities graphically. Solving equations, I don't know why I capitalized that. Solving equations and inequalities graphically. So here, I've got a screenshot from Desmos, and so this is from 29, which part A we looked at was 16x to the power of 3 plus 16x squared. Oh, I guess I need a little bit more room here. There, then I can go into, where is it equal to x plus 1? Well, it's going to be equal to x plus 1. So here, the purple graph, that's your 16x to the power of 3 plus 16x squared. Okay, so it looks like this. Looking at the highest power of x to the power of 3, it's behaving the way we think it should, right? Remembering those general graphs, x to the power of 3, we're expecting something like this, and that's what we have in the end point. So now, because we also have this x to the power of 2, it'll do some stuff to the middle, but if you look at the highest power of x, that's the end behavior that you're gonna see. So knowing the shape of x to the power of 3, right, we know it's gonna behave like this, and then because it's not just x to the power of 3, right, it'll have some activity here in the middle, but the end behavior, right, is really important to know, right? And so then we have x plus 1, which is just a linear equation, right? The highest power of x is 1. So here we've got the straight line, and if we're looking at where are they equal to each other, right? I had clicked all these points here, and so they're equal to each other at x equals -1, x equals -0.25, and x equals 0.25. Right? Part B of that question was, where is 16x to the power of 3 plus 16x squared? Where is it greater than or equal to x plus 1? Well, we're talking about the outputs of these things, right? So what values of x give outputs that are larger for the purple graph than for the straight line, x plus 1? Well, so this thing is going to be greater than or equal to, starting at x equals -1 and going to x equals -0.25, right? And then here, all these purple outputs are less than the straight line, right? All the way up until this point, and then it picks up again at x equals 0.25, all the way to infinity. Even though it looks like they're kind of tight on the y-axis, these things will eventually spread out and cover to infinity and negative infinity. So even though it doesn't look like it, the domain of this thing is going to be negative infinity to positive infinity, or the set of real numbers. Okay, so that's where we ended off last day. We can talk about increasing and decreasing functions. So here, and it's exactly what you think it is, so you already know what it is. If I asked you, hey, where's this purple, oops, drawing on the graph, where's this purple graph increasing, right? You would probably guess from negative infinity up until this point, which I didn't click on, so I don't know exactly where that is. But this is where it's increasing, and then it hits the cusp, and then it starts decreasing, there, and then it jumps back up, so it's increasing, right? So we already kind of know and understand when a function is increasing and decreasing. So let me see, gotta grab these notes here. So here, kind of by definition, f is increasing on an interval I, so any interval I, if the output at x1 is less than the output at x2, whenever x1 is less than x2. So, but what that looks like, right, is this upward slope, okay? And then same thing with the downward slope, and you can kind of convince yourself that, okay, if you've got this downward slope, if x1 is less than x2, and it's going down, then the output for x1 must be larger than the output for x2. Right, f of x1 is greater than f of x2. So maybe up above here, we already have a good idea about when functions are increasing or decreasing. Oops. How come it? Okay. Clean this up. When functions are increasing, there, or decreasing, but we could consider the following definition. Well, now I've done it again, didn't I? Yep. Sure did. But we could consider the following definition. Right. What I'm saying here is I don't want you to spend a lot of time kind of memorizing this or anything, especially because your tests are all open book essentially. And so just have it handy, right? The only time that I'll get you to figure out if something's increasing or decreasing, I'll give you a graph and ask you, hey, where is this thing increasing or decreasing? What this is leading to, increasing to, is the local maximum and minimums. So of course, at this point, so here this graph is increasing, increasing, and then at this point, which seems to be a local maximum is what we call it, that's where it changes direction and it goes back to decreasing, right? And then same thing here at this local minimum, this is where it changes direction from decreasing to increasing, right? So at these points, that's where we find these local maximum and minimums. Now these are going to be important in different applications, right? So if you're trying to maximize your profit, for example, you want to figure out what this point is, right? What do I need to do down here to make it the maximum profit? If you're trying to minimize costs, then you want to be down at the minimum, right? And so I use economics examples, right? But you could talk about populations. Where is this population maximized? Where is it minimized? It has all kinds of applications, right? So the maximum and the minimum, typically if you're modeling something, they mean something and they're going to be important. So where it's increasing and then it switches to decreasing, technically that's your maximum or minimum. If you have a graph though, you can just look at it and figure out where your maximums and your minimums are, right? So it's not too bad. And again, just like increasing and decreasing, we have a pretty good intuitive idea of what a maximum is and what a minimum is. The only difference here is that this is what we call a local maximum, because clearly this graph keeps going and it increases, presumably to infinity unless it plateaus. But for us, this graph would just keep going to positive infinity. And so this isn't really a maximum, right? This is higher than this point, but that's why we call it a local maximum. Same thing with here, we call it a local minimum. And when we're putting that local maximum minimum, we're just saying, hey, we don't know what happens beyond, you know, the range that we've looked at or the domain that we've looked at. So we know that a maximum value, I'll put in brackets a local maximum, will occur where the function switches, I'll put switches because it's not really like a term, but it switches from increasing to decreasing. From increasing to decreasing. Right? If you've got a graph like this, we would probably say this is the maximum. We could call it a local maximum, but just for brevity, I'm going to just call it the maximum. And then so here, right, it's increasing. And here, it's decreasing. Other way around for the minimum, right? And so we've got this little blurb here. In fact, I'll just make it take up the whole page. Okay. So notice that we call them local maximums, right? This is a maximum, this is a maximum. This maximum is larger than this maximum, but also because we've cut off our graph, the graph probably extends, right? So that's why it's not necessarily the overall maximum or the overall minimum, because they kind of keep going, right? But for some range of interest or some domain of interest, I should say, these are maximum values and these are minimum values, right? So we can pull in the definitions, right? The function notation definitions. So the function value f of a is a local maximum value if f of a is greater than or equal to f of x when x is near a. So if f of a, so here we've got this point a, and then all the other values are just f of x's, right? What it's saying is the output at f of a has to be larger than the outputs of all the other x's around a, right, when x is near a. So I'll remove that because it's not, because we use the same a later on for the minimum, so it could get confusing. Same thing with the local minimum, right? If f of a, so now our a has moved to here. If f of a is less than or equal to all the other outputs at the x's around a, then you have a local minimum. Let's have a look at some of these. maybe I'll just copy 2 of them, save some space, because I'm only going to use probably 1 of them. Oops. Come on. There we go. So the graph of a function f is given. So here we have this graph. It's safe to assume that these things keep going, right? So typically we don't put the arrows on there because we just always assume that, you know, we've zoomed in on the graph of interest. But just so you keep track, right? These things keep going and going. So use the graph to estimate the following: all the local maximum and minimum values of the function and the value of x at which each occurs. Of course, you could, if you have a function, you could graph it in Desmos, and then you can just click on the little dots because Desmos will just highlight, hey, here's your maximum, here's your minimum. And so it knows that these are points of interest. And so if you have the function, which we don't in this case, we just have the graph, that's fine. Then you can just use Desmos to find those maximums and minimums. Okay. Just as a side note, these are functions, right? Because if we draw these imaginary vertical lines doing the vertical line test, well, I'm only crossing the graph at 1 point for each value of x. So it is a function. Same thing for this one. Nice. So we want to figure out where all the local maximum and minimum values are. So this here looks like a max. And this looks like a min, and this looks like a min. Of course, they're only local max and mins. Potentially they're, you know, real minimum values because it seems like the function is just going to keep increasing and increasing, but we're not going to bother with that. We're just going to call them local max and mins. So we need to figure out what value of x these things happen at, and we may as well figure out what the output is at those points. Okay. So here for this maximum, well, this is at 0, so x equals 0, and I would assume y equals 2, since this is 1, and then I've gone up another one, so 2. For this not so minimum, right? It's a little bit higher than the other minimum, so let's deal with this one first. This is at a value of x equals 2 and a y equals 0. And then for the last minimum, it looks like I'm at x equals -2 and y equals -1. Okay. The intervals on which the function is increasing and on the which the function is decreasing, right? So it's increasing. Let's see here. Here it's decreasing, increasing, decreasing, increasing. Okay. So for, let's put it over here, 43, where is it increasing? We'll use interval notation, right? So it's increasing, we said from here to, so from x equals -2 to x equals 0. And then it's increasing again from 2, so x equals 2 to infinity. I'm going to use round brackets. Technically at the maximum and minimums, the slope is 0. So it's not increasing or decreasing. But if you wanted to use square brackets, doesn't matter. I'm just going to use round brackets. And then where is it? So here I'll just do increasing. So that was here. and here. And then we'll do decreasing in green. So it was decreasing here and here. So from negative infinity, infinity has to have a round bracket. So negative infinity, positive infinity, they're not actually numbers. So that's why we can't include them. So they have to have round brackets. So negative infinity up to -2, union from 0 to 2. Nice. So maximum, minimums, increasing, decreasing, these are things that, you know, don't doubt yourself. You know these things just kind of intuitively. Looking at a graph, you know what they are. But it's nice to see kind of function notation incorporated with it, right? And then so we can get used to it. And so it's nice to take a concept that we understand and then apply the function notation to it. Okay. So, oh no. What can I do here? We're going to start a new section, so that's why I usually start a fresh page, but I'll do it down here. Seems like a waste of space. The average rate of change of a function. So we talked about the net change, right? That was in our review here. The net change of a function is f of b minus f of a. The average rate of change is the net change over the change in x, right? So in this case, the change in x would be b minus a, right? So the average rate of change is not that crazy. We'll steal this little blurb here. Whee! Okay, so the average rate of change of a function y equals f of x between x equals a and x equals b is defined as f of b minus f of a over b minus a. Notice though that this, and maybe I'll use light blue, this is the net change, right? So the average rate of change is the net change divided by the change in x. So we're talking about the secant line. I don't really expect you to keep track of the secant line, the tangent line, all that fun stuff. That would be for calculus when you take it or if you take it. But the secant line is just a line that connects 2 points. So you just take a straight line. So you pick 2 points on your graph and then you connect them with a straight line. That would be your secant line. Okay. So the average rate of change is essentially the what did I want to say here? The net change over the change in x. I don't know why I built up to that. Okay, let's do a couple of questions or one or two because it's not really that crazy. Let's do, now I'm running out of room. There. How about that? Okay, so let's do 13 first. It's got a little fraction in it, right? But I'm really pleased with, so I didn't finish marking your tests, but I will finish today, come hell or high water. But I'm really impressed with your guys' fraction work. So nice work, and it makes me really happy. So good job. You'll get an email once the tests are marked from Gradescope. So for 13, h of t is negative t plus 3 over 2, and we're going between t equals negative 4 to t equals 1. Yeah. And we want to find the net change and the average rate of change between the given values. And so we don't need to know really what this looks like, although you easily can using Desmos, right? But we want to figure out what the net change is. So the net change is in general f of b minus f of a. In this case, a is negative 4 and b is 1. And b is 1. And in this case, we're not dealing with a function f, we're dealing with a function h. So this becomes h of 1 minus h of negative 4. So we need to evaluate h at t equals 1 and then subtract h at t equals negative 4. So we want to keep these things separate, and in fact, if you find it easier to evaluate h of 1 and h of negative 4 separately and then put them together, that's totally fine. I'm going to keep them separate by big brackets, but I am going to keep them together as a net change. Negative 1 plus 3 over 2 minus negative 4. Oh, sorry, negative 4. All right. Negative 4 plus 3 over 2. Maybe I'll put brackets around this 1 just to indicate that that was the one I inserted. Okay, so now, right, I need a common denominator here before I can subtract two fractions essentially, right? And so what I have is I have negative 1 over times 2 over 2 plus 3 over 2 minus negative 4, I'm just going to write as 4 times 2 over 2 plus 3 over 2. What's nice is, of course, these are going to have the same common denominator, so it eliminates a lot of work because I am still dealing with the same fraction, right? Unless I was introducing a fraction over here, that would make a mess, but I've got the same common denominator, so it's good. So now I'll be able to subtract these things. So I've got negative 2 over 2. In fact, I'm just going to put them over that common denominator right away. Negative 2 plus 3 over 2 minus 8 plus 3 over 2. Negative 2 plus 3 is 1 over 2, minus 8 plus 3 over 2 puts me at 11 over 2. 1 minus 11 over 2, they're both over 2, so this is the same as 1 minus 11 over 2 is going to be negative 10 over 2, which should put me at negative 5. So the net change is going to be -5. Now, the average rate of change is going to incorporate, well, how much did I change from going from A to B, right? A change of from -4 to 1, right? That's a distance of 5. And I managed to change kind of vertically -5 units, right? And so my average rate of change, the average rate of change is f of b minus f of a divided by b minus a, which in our case is h of, h of 1 minus h of -4 divided by 1 minus -4. We already know what h of 1 minus h of -4 is. We know it's -5. So this is -5 over 1 plus, 1 minus -4 is 1 plus 4, which is 5. So we've got an average rate of change of -1. So this is good. Let's do another one, just to solidify things. I was gonna jump ahead to the linear functions because they're the easiest. In fact, we just use the linear function. But I'll hold off. Let's do another example. Let's do, you know what? Let's do 20. In fact, I'm gonna kind of steal it here, copy. Oops. Okay. So what's weird about this one, right? We're going from x equals 2 to x equals 2 plus h. So we're not saying what h is, right? We're just moving a distance of h from our starting point of 2. So we start at 2 and then we went to 2 plus h. So we've just moved a distance of h, right? Moved a distance of h, so some arbitrary h. Let's find the net change is f of b minus f of a, which in this case, right, we have a function f and our a is 2 and our b is 2 plus h. So here, what this becomes is f of 2 plus h minus f of 2. You might remember those difference quotients that we were working with. This is part of a difference quotient. It's not important for now, but I'm just pointing it out that we've seen something like this before. In fact, we've seen something more complicated than this before. So f of 2 plus h, wherever I see an x, I'm gonna plug in 2 plus h, right? And I'm gonna just highlight that these are two different functions that I'm subtracting from each other by these square brackets. So 1 minus 3 times 2 plus h squared minus, square bracket again, 1 minus 3 times 2 squared. Keeping in mind, right, we've got to be really careful. 2 plus h squared is 2 plus h times 2 plus h, right? So I don't want to see you bringing in this power inside. That's illegal math. 1 minus 3 times 2 plus h times 2 plus h. I always write it out like that because it just reminds me that I need to expand this thing and it's going to be bigger than I probably want it to be. 1 minus 3 times 4 is 12. So I'm just going to simplify that as I go along here. So now what I'm going to do is I'm going to expand these, this 2 plus h squared, and then I'm going to multiply it by 3. So I'm going to keep the 3 outside. And so I've got 1 minus 3 times 2 is 4. 2 times h, 2h plus 2h plus h squared. Now, you might be comfortable putting this 2h plus 2h together immediately. That's totally fine. For some reason, I always like to take it slow, even though I know it's going to be 4h in the middle here. I always just write them out just to convince myself, I guess. And then minus 1 minus 12. 1 minus 12 is negative 11. We've got time. We've got a lot of work to do here, so I can take it nice and slow and simplifying this side. So we have 1 minus, and then 3 times, so I'm going to bring this in. I'm going to smush this together. Nah, I'll show this extra step. You don't have to, but 3 times 4 plus 4h plus h squared plus 11. So now I have 1 minus 12. And what I'm going to do is I'm going to keep this negative outside because I don't want to forget about it, right? I have to bring this negative onto each of the terms. So the first thing you could do is you could multiply each term by -3, but you have to remember to keep that negative on there. So just to make sure that I do that, I'm going to keep that negative outside and keep everything in brackets and just multiply by 3 when I bring that in, just to make sure I don't forget about it. Plus 12h plus 3h squared plus 11. Now I'm going to bring this negative inside. So I get 1 minus 12 minus 12h minus 3h squared plus 11. Notice that I ditched the brackets because I don't need them anymore, right? I'm almost at the end here where I'm combining these things, so that's why I got rid of those brackets. So now I've got 1 minus 12 plus 11. 1 minus 12 is negative 11 plus 11. So I get negative 11 minus 12h minus 3h squared plus 11. But just to highlight, negative 11 plus 11 goes away. So now I've just got negative 12h minus 3h squared. And you guys were really good on the test about writing things with decreasing powers. Sometimes even I get lazy, and but it's good to get in the habit of just writing these things with decreasing powers. So I'm going to rearrange this and say, well, that's going to be equal to negative 3h squared minus 12h. Looks like I can pull out a common factor of negative 3h from here. I'm going to hold off on that, mostly because I know where we're going here with the average rate of change, right? You'll see what I mean in a little bit here, but just for practice, this is the same as negative 3h times h plus 4. Right? Pulling out that common factor of negative 3h. So now for part B, sorry, not the net change, that we already did that. The average rate of change is f of b minus f of a over b minus a. Now, we just found what f of b minus f of a is, right? So that's not the hard part. In fact, we're done with the hard part. F of b minus f of a is this, and I'm gonna just steal it so I remember. Copy. So this is gonna be f of 2h minus f of 2 divided by 2 plus h minus 2. We just found what this is, right? So I'm gonna steal it from up here. This is gonna be negative 3h times h plus 4 divided by 2 plus h minus 2 is just gonna be h. And because I was able to pull out this common factor of h, I can actually cancel these, only because I'm multiplying all the way across here, right? So what I get, my average rate of change is negative 3 times h plus 4. That's it. So the average rate of change is very familiar for linear functions, but it's just telling us how fast is something increasing or decreasing, right? If it's negative, it's decreasing. If it's positive, it's increasing. And so it just gives us an idea of how steep this thing is. Even if there's a curve to it, how quickly are things changing? In 2.5, we're talking about linear functions. Linear functions are just straight lines, y equals mx plus b. We've already worked with them. In fact, it was in section 1.10. And so you know how to graph a line, right? You just need to find 2 points on the line. So you pick any 2 values of x that you want to work with, you plug them into your function or your linear equation, and then you can plot those coordinate points that you find. And so the only really kind of new thing is talking about the slope and the rate of change. So for a linear function, it's kind of special. It's not that crazy though. But let's say here is 2.5, which is linear functions. So for a linear function, notice that this is essentially y equals mx plus b, right? The slope of the graph of f and the rate of change of f are both equal to a, which is the slope, right? So a, we're used to calling it the slope. Whatever's attached to the x here, y equals mx plus b, m is the slope. M is attached to the x. And so a is the slope of the graph of f, and which is the same as the rate of change. Okay? We said that this first example that we did, right, here we have a linear equation. X is t in this case, but that's okay. Our slope would be -1, right? Our y-intercept is 3 over 2, that's fine. Our slope is -1. What did we find our average rate of change to be? -1, right? So we've already seen this in action, and it's just a nice, pretty, I guess, obvious result. If you've got this straight line and you're taking a point on it and a point on it and you're finding the average rate of change here, well, that's the same thing as finding the slope, right? And so that's all we're saying in section 2.5. So here, if you have a linear equation, right, something like y equals mx plus b, or that you could rearrange to y equals mx plus b. Typically you're looking for the highest power of x can only be 1, right? You have to have a y in there, right? So if you're able to rearrange it into something like this, then if you have a linear equation y equals mx plus b, the slope of the line is also the rate of change of the line. So nothing too crazy here. Which one of these examples do I want to do? All of these here are just kind of, I don't want to call them basic, right? But we're just graphing straight lines, which we spent a lot of time doing in section 1.10. So you can use Desmos if you want. Let's see here. Let's do one of these. Let's do, I'm going to do 24. The only reason I'm picking this one is because it's got kind of strange notation. We're not used to seeing capital A of R and things like that, but it's still function notation. The name of the function is just capital A, whatever that is. R might be some, I'm going to guess radius, right? The area as a function of the radius, potentially, right? Something like that. Looks a little bit weird, but so here, we've got this function. As long as you remember that whatever you're putting in as your input, you can think of it as your x, and then A of R would be essentially your y, right? And so here, for 24, we're given that A of R is -2/3R minus 1. Okay. Let's just make a note here. This is a linear function. Of the form y equals mx plus b. Right. The slope here is going to be -2/3. Right? So we know we have a negative slope, so that means it's going like this. I guess it's going like this. Shouldn't do this and this. The slope is -2/3. Okay. So here, if we have to sketch the graph of this thing, well, first thing we could do is we could use Desmos, right? Or we could practice just sketching it by hand. Okay, so first thing I'm gonna do is I'm gonna sketch it by hand first, just for some practice, because it's been a while. Right, so sketch by hand. Remember how we draw a straight line? So once we've figured out that we have a linear equation, we know it's going to be a straight line. So all I need is 2 points, at least 2 points on the line, and then I can connect them with a straight edge and extend the line. So what I'm going to do is I'm going to make a table of values, or sorry, I guess it's R. R gives A of R, which is -2/3R minus 1. Now, I want to pick convenient values of R, right? So my go-to is R equals 0. R equals 0 makes this term go away, so then I just have A of R must be -1. So I'm going to use that first. A of 0 is -1. The next thing I'm going to do is I'm going to pick another convenient value of R. In this case, because I'm dividing R by 3, I should probably pick a multiple of 3 just to make my life a little bit easier. So if I let R be 3, A of 3 is negative 2 over 3 times 3, and then minus 1. Well, 3 over 3 is going to go to 1, so negative 2 times 1 is negative 2. Negative 2 minus 1 is negative 3. So my points here, my x, y coordinates, even though it's R, A of R, on the graph, I'm going to put them on the x and the y axis. And so I've got 0, negative 1, and 3, negative 3. Oh, I keep forgetting that I've got these fancy stickies in here. I need a little bit more room here. And for my x values, what I have is x is 0 and x is 3, right? And then I've got a y of negative 1 and negative 3. So I'm just surveying the scene to figure out where to put my axes on here. So I know I need to make room for y equals negative 1 and 3. So what I'm going to do is I'm just going to put my x-axis here and my y-axis here, and I'm going to use negative 1, negative 2, and negative 3. 1, 2, and 3. So my first point is at x equals 0, y is negative 1. So here at x equals 0, 0, negative 1 here, and then maybe I'll do these in green, 3, negative 3. When x is 3, y is negative 3. So now I've got this straight line as soon as I connect these, which I'll use the, I don't know, the edge of my calculator, I guess, to connect these dots. And then I extend the line because, of course, the line goes on and on and on to infinity and negative infinity. Oh, it's on the next page here, which is not what I want. So there. Okay, so we sketched the graph. So sketch the graph, we did it by hand. Let's just confirm with Desmos. So negative 2 over 3, in place of r, I'm going to use x. Did I show you guys there's a Desmos calculator out there? It's free, obviously. It's okay. I wouldn't say it's as good as this one. So you guys have this one probably. It's got a couple more functions, but if you're in a pinch. So we've got negative 2 divided by 3 times x minus 1. Okay. So that's the function that we had, this linear function. It tells us where it crosses the x-axis, where it crosses the y-axis. But then we can also just confirm our points, right? So here we found that when x is 0, y is negative 1, right? And so that's one of the points. And then let me just try to get the point on here. When x is 3, y is negative 3. I can't seem to get it to stay there. There. Anyways. So it looks like we got the same line, right? That's a relief. So now we're going to find the slope. right? And then find the rate of change of the function. The thing is, we know for linear functions that the slope is the rate of change. And we already know the slope from the equation. It's -2/3. So what I'm going to do is I'm just going to have part B is the slope is -2/3. And the rate of change is also -2/3 because it's going to be the same as the slope. Good. All right, we are doing great. I haven't seen a single question. Everyone's having a quiet morning. That's all right. So I think that was the end of functions part 1, but I did post functions part 2, so I'm just gonna go grab them here. Yeah, I know. Let's log in, of course. So functions part 2, I'll bring those in. Oh, I almost sent it to myself again. Okay. So we're going to talk about transformations of functions. This is a lot of, well, it would be memorizing. If you had to memorize things, usually I would let you make a formula sheet, but of course you have all your resources for all your tests. And so this is going to be one of those handouts that you're going to want to keep on hand, right? Because there's a lot of stuff going on here. And look at all these blue boxes. What a mess, right? And it's just talking about how can we transform a graph, right? And so how do we change a graph? Because it's not always going to be this beautiful y = x squared, for example, right? We could have y = x - 2 squared. And what's that thing going to look like? So 2.6 is on transformations of functions. Okay. So knowing what the general shape of an overall function looks like is going to be really helpful in figuring out how these things transform. And so knowing, oops. Knowing the general shape of common functions will be really helpful in dealing with transformations of functions, in dealing with transformations of functions. So, for example, so we've got all these little blurbs here. First thing we're going to talk about is vertical shifts, right? So shifts up and down. So these are shifts up and down. Okay, so let's talk about, well, up and down. So if you're moving a graph up or down, so if you've got this general y equals x squared, right, a nice parabola here, then if you change the y values, right, which is f of x, then what you're doing is you're either adding or subtracting values to the y's, right? So what that looks like is if you have f of x plus c, then you're going to shift the graph of y equals f of x, so that default y equals f of x, up c units. And so from here, the blue graph is y equals f of x. And then if we're doing y equals f of x plus c, then everything just gets moved up by c units. Same thing if you've got f of x minus c, then the whole graph gets moved down, but not smushed or anything like that. We will talk about kind of stretching and compressing graphs, but for now, everything just gets moved up or down. Okay, so that's if you have, if you're adding or subtracting a value to the whole function. Add or subtract a value to the whole function f of x. Okay. We can talk about horizontal shifts of graphs. Horizontal shifts are, of course, kind of the same, but horizontally. Okay. Now, because you're shifting to the left or to the right, the value that you're manipulating is x. And I always find it a little bit counterintuitive, but if you subtract c from x, what happens is things move to the right, even though I, at least intuitively, would want it. Okay, so if I'm looking at x minus c, I would probably think that it would move to the left, but it doesn't. Okay, so here, that's kind of important, right? So if you're subtracting c from f of x, it actually moves it to the right. And if you're adding c to x, then it moves it to the left. So these can be kind of counterintuitive. Can be counterintuitive. At least for me, right? I always find that it's a little bit backwards. But that's also how I remember it, right? It's like, oh, the x one, though, it works the opposite of how I want it to work. So just kind of having some sort of a trigger, right, helps. So this does assume that c is greater than 0, right? So it's kind of saying that c is behaving the way you think it is. So x minus c, if c was less than 0, right, x minus -4, for example, is x plus 4, but that's the same as x plus c, right, if c is 4. So it's just saying that, okay, well, c is going to be positive just so that the negatives and positives behave the way they say they are here. So we can shift left or right if we add or subtract a value I'll say 2x, even though it would be from x if it's subtracting, but that's okay. Okay, so x on its own, so not f of x. Notice the difference here. Okay, so far so good, right? Kind of horizontal shifts, vertical shifts. I did those backwards. Horizontal shifts, vertical shifts. Let's do a little example here. Let's look at this one here. So what we can do, or what we often do, is we start with some base graph, right? So if we start with y equals the root of x, the y equals the root of x is, it looks like this, right? And it's on that list of functions that we should probably have a good idea of what it looks like. It wasn't one of the highlighted ones, I don't think, or did I put roots? It was the first three. Now I want to make sure that I did. It was, right? So we should know what the roots look like. So we start with this basic y equals root x. So then what we can do is we can say, okay, well, if I do the root of x minus 3 actually behaves different than what I want it to do, right? So what happens is everything, this whole purple line gets shifted over by 3 units to the right. Right? And then if I wanted to, what I could do is I could take, okay, so now I've got the root of x minus 3. So now I'm starting from this blue graph, right? And then if I do the root of x minus 3 plus 4, well, what happens is I have to move this, all these y values up by 4 units, right? So we can combine vertical and horizontal shifts. We can combine vertical and horizontal shifts. Okay. Usually by building out from the original function, right? So if I want to end up at this graph, what I would do is I would start with the root of x, right? So the very basic graph, and then I would do x minus 3. Okay, so that shifts it to the right 3, and then I would add 4, right? So you want to start from the most basic graph, and then you build out. So we can combine vertical and horizontal shifts by starting with the most basic graph, right? In this case, the root of x, and then transforming it piecewise, right? So, and then transforming it, kind of blooming out, and transforming the graph in stages, right? Starting from that basic graph and moving out. Start from the basic graph, or I'll say function, the basic function. And I always like to think of it as blooming out, right? So from root x, I'm moving to root x minus 3, and then I'm moving to root x minus 3 plus 4, and blooming out. Okay, so those are pretty core, right? We need to be able to shift graphs up and down and to the left and to the right. Some other things that we can do, right? We can reflect graphs. Okay. So if you have a graph of y equals negative f of x, so in this case, f of x reflects the, or I shouldn't say reflects, reflecting graphs, who's incepted. If you've got a basic graph of f of x, but you want to graph negative f of x, what happens is you're going to reflect the graph, so the original graph, you're going to reflect it in the x-axis, right? So here, if you've got y equals f of x, then y equals negative f of x is just going to be it flipped on its side, right? So reflecting in the x-axis, right? So your kind of rotisserie is on the x-axis, whereas if you've got a negative x, right? So here you've got a negative f of x, and here you've got a negative x. If you've got a negative x, then your rotisserie is on the y-axis instead, right? Because all these, this previously positive x value is now going to become negative x values, but the y values stay the same, right? Here we can think of it as, okay, so all the x values stay the same here, but the y values go from positive to negative, right? So in y equals negative f of x, the x values stay the same, but the y values, right? And remember, y equals f of x. So if you've got negative f of x, right, then your y values are flipped to negative, right? And that happens around the x-axis. And then in y equals f of negative x, right? So here, the x's are negated. And so now the y values stay the same, but the x values are flipped to negative. Let's see if I have a... I don't think I have a good example quite yet. And here. So we'll talk about the vertical stretching and shrinking as well as the horizontal stretching and shrinking. And after we've talked about even and odd functions, then we've got a really good handle on all the things that we could do. Okay, so this one, I made it a little bit bigger just because we need to be able to see it properly. And there's some nitpicky stuff in here. So if we've got a graph of y equals c times f of x, so now just remember, okay, so c is going to be some number that I'm going to multiply by my y's. So the y's, right, are kind of, they're vertical, right? And so what I'm going to say here is, maybe I'll put it on the, maybe I'll shrink it down just a little bit. Give myself a little bit more room here. Multiplying the f of x by a number c, right? So f of x is, these are the y's, right? So that's what gives you this vertical stretching or shrinking. Gives vertical stretching or shrinking. The key is if C is greater than 1, right? So if C, so this number that you're multiplying the function by is greater than 1, then it's going to expand your y values, right? So from here, you've got y equals f of x. So here's our original function. And then when we multiply it by C, it gets amplified, right? And that's how amplification works. It gets amplified by a multiple of C, right? So all these y values are going to be multiplied by C. Whereas if C is between 0 and 1, so if you've got a decimal value for C, then it shrinks the graph, so it just kind of smushes it closer to the x-axis. So here again, our y equals f of x is the blue graph. And then if I'm shrinking it, then I get this kind of tighter graph around the x-axis, right? So we need to keep track of whether C is greater than 1 or if it's between 0 and 1, because it's going to behave differently. So next one, very similar, is going to be on horizontal shrinking and stretching. Right, so now again, right, we're multiplying our x, which is the horizontal, right? So as long as you're manipulating the x inside a function, then what happens is horizontal, right? Whether it's stretching or shrinking or movement, right? If you're manipulating the x, it's gonna move horizontally. Whereas if you're manipulating the whole function, then it's gonna move vertically, right? So whether it's stretching, shrinking, whatever, up, down, doesn't matter. So again, we have these conditions, right? If C is greater than 1, then, and again, the horizontal action works the opposite of how I would intuitively think that it would work, right? But maybe that's a nice kind of check-in point. So here, again, multiplying the x by a number gives horizontal stretching or shrinking. Okay. So if you've got f of 3x, for example, what happens is your original f of x, right, is this nice lofty blue line, whereas y equals f of 3x, for example, right, is going to be this kind of smushed together function, right? So it's going to smush it by 1 over c. Whereas if c is between 0 and 1, then we get this kind of elongated function, right? Because notice that it still goes to the same minimum and maximum, right? So the same maximum and minimums are here. It's just the values that they happen at are either smushed together or elongated, right? So nothing happens to the amplitude. That's for c times f of x to do, right? So we need to keep that in mind, because often, at least in my mind, if I'm thinking about shrinking something, right, then I want to shrink the amplitude as well, but that only happens if I'm multiplying the overall function. Good. So the last kind of, well, I don't want to promise See what it is. The last kind of concept here are even and odd functions. We've already talked about even and odd functions because I told you that in that general shapes of the graphs section, right, we've got these even powers of x. Well, if we've got even powers of x, then they're all going to basically look like this, right? And if we've got odd powers of x, then they're all basically going to look like this, right? And so that's what we're seeing here. If we've got an even function, then it's symmetric, right, around the y-axis. It can get moved over, right, up, down, but in general, if you kind of plopped it down, it would be symmetric around the y-axis. Whereas here, an odd function, well, x to the power of 3, for example, right, it's going to be symmetric around the origin, which is a little bit harder to think about, right? But I imagine this arm kind of gets swung around here, and so that's how it's symmetric. But I actually think it's really hard to think about symmetry around the origin. So that's why I tell you, okay, if you know what an even function looks like, well, it looks like this. If you know what an odd function looks like, it looks like this. Okay, you can prove that you have an even function by plugging in negative x and seeing if it ends up being the same as positive x, right? So f of x equals x squared, for example, right? F of x equals x squared. Well, we know this is an even function because the power is even. So I'm just telling you that it's an even function. In fact, if the highest power is even, it's an even function. If the highest power is odd, it's an odd function, right? So f of x equals x squared. If you do f of negative x, well, negative x squared is the same as x squared, which is equal to f of x. Therefore, f of x equals x squared is an even function, right? Just a quick proof, I guess, of how these things work. So we just need to be aware that we can have even or odd functions, and it's going to determine what the shape of the graph looks like. Okay. So what I want to do is one of these, or at least one of these, problems. If you keep going through the notes on the next page, right, a lot of these just have graphs that are given to you. So I'm going to leave that for you guys to work through on your own, right, and just kind of see how if you can identify these transformations. I labeled this as optional because I don't want to spend too much time in here. It is an important skill to be able to graph stuff. At the end of the day, if you can graph something in Desmos, that's going to be really useful, right? And so you can try these, right? It's going to be a really good skill to have, at least if you can look at a graph and say, oh, it should look something like this, right? To check your work, you can use Desmos. Same thing with here, right? All of these are just kind of more exercises on what we're doing. So there's nothing really new here. Once we've introduced how we can transform all these graphs, they're all the same. So we're just going to do a couple of these exercises here, and then you should be able to do the rest of the exercises on your own. Let's do, so it says, suppose the graph of f is given. Describe how the graph of each function can be obtained from the graph of f. And so if you've got a default function f or f of x, then we're given some of these transformations, and we're just going to talk about what these things would look like, right? So we don't know what F looks like, but we can start here, right? So if we've got, let's do 7a, for example, f of x minus 1, right? You'll want to have those notes that we just went through handy, right? Because here, this looks like y minus 1, right? So it's going to be a downward shift in y. So move all the y values down by 1 unit, right? Minus 1 moves it down. Because remember, vertically, the y values behave the way you think they will. The x values, they're the rogue ones, and they just kind of do the opposite of what you want them to do, at least for me. How about 7b, f of x minus 2? F of x minus 2, so now we've got, we're not really subtracting 2 from each x because it works, like I said, the opposite of what you want it to do, right? But we do have, so c in this case was 2, right? So we've got f of x minus 2, 2 is greater than 0, fine. So what we're going to do is we're going to shift the graph to the right 2 units. Shift the graph to the right by 2 units. Let's do one that's a little bit more involved, maybe. How about 13? So if we're looking at 13, 13a, I'll just copy it from here. Y equals negative f of x plus 5. Okay. I want you to start at the core function, right? F of x, whatever it is, whether it be x to the power of 3, x squared, whatever this function is, it doesn't matter. As long as you remember what those general shapes look like, right? Then we can keep track of what's going on here. And then from here, you're going to bloom out, right? So you've got this basic function, and the first thing you're going to have to do is you're going to have to take the negative of all the y values. So here, what this is doing here, where was it? Yeah. Y equals negative f of x, right? You're going to reflect all the values in the x-axis, right? So all your positive y values become negative, and then of course if you have negative values, if you negate them, they become positive. So things revolve around the x-axis. So here, this says first reflect about the x-axis, right? Or we can think about make all y values equal to negative y. Right? If it's positive, it becomes negative y. If it's negative y, then negative y is just y, right? So that's how we reflect around the x-axis. And then after we've done that, then we can move this whole thing up by 5, right? So then shift the entire graph, right? Because we've got plus 5 on the whole f of x. So then shift the entire graph up 5 units. Good. What if we have 13b? Y equals 3 times f of x minus 5. Okay. This is very similar to what we just did, right? But now I'm multiplying my y values by 3, right? And then I'm moving everything. So once I'm done that, then I shift everything down by 5 units. So multiplying the y values by 3, just so we know what to expect. Let's go back here. It's going to be a vertical stretch. And so y equals c times f of x. If I've got c greater than 1, which I do in this case, 3 is greater than 1, then I'm going to stretch the graph vertically by a factor of c, right? So what's going to happen is all my y values become 3 times f of x, right? So all my y values get multiplied by 3. So the first thing we're going to do here is multiply all y values by 3. And then the second thing I'm going to do is move the entire graph down 5 units. Move the entire graph down 5 units. Just wrote 3. Okay. What if we did, let's have a look at 16a. And then probably 18a, right? I'm not gonna do b, I'm just gonna do 16a because they're very similar, right? So we've seen enough of those. 16a is 1 over 3 f of x minus 2 plus 5. Okay. Remember, you're always going to start at f of x. The first thing that happened to this thing is we subtracted 2 from x. But remember, that moves it to the right by 2, right? So first thing you're going to do here is shift the entire graph to the, 2 units. 2 units to the right. Okay, so that's the first thing that happens. First you do that shift because that's how things are being applied to this function. Next thing that happens is I'm multiplying by 1 over 3. So let's just remember that this 1 over 3 is multiplying the y values, right? So now these y values are going to decrease by 1 over 3. If you go back here, where is it? Here. So 1 over 3 is between 0 and 1, right? And so it's going to shrink the graph by 1 over c. And so now what we're going to do right here, shrink the graph by multiplying each y value by 1 over 3. And then to this whole function, we're adding 5. So that means that I've shifted things to the right, and then I've shrunk them, and now I'm going to shift them up, right? Pretty big changes in in this function, move the entire graph up 5 units. And then I said we would do 18a just because I want to manipulate the x a little bit more than adding or subtracting. So for 18a, I've got y equals f of 2x minus 1. So again, we start at f of x and we just see what's been applied first. So 2 times x is the first thing that's happened. So let's go back here because when we're changing the x, it's just good to double check that you've got it right. And so c in this case is going to be 2. So 2 is greater than 1. So it's actually going to shrink the graph horizontally by a factor of 1 over 2. Right? So all your x's are going to become x over 2. Right? So now, right, it's going to shrink the graph. So the first thing we're going to do here is shrink the graph horizontally by multiplying each x value by 1 over 2. Right, so now it's going to be shrunk like this, not vertically. Vertically it stays the same, but it's just shrunk in like that. And then f of x minus 1 says, okay, well now what you can do is you can move it down 1 unit. So move the graph down 1 unit. Good. Okay. So let's see here. Like I said, I'm going to leave all those kind of these problems where you're given a graph. The absolute value of x is this V shape, right? So I guess that helps, but if you're given a graph, knowing what these changes look like, right? Like we just talked about, we talked about all the different scenarios. You should have a pretty good grasp of how these things are going to change. So I guess I was going to get into the optional stuff, but I labeled it optional, so I'm not going to do that. But definitely have a look and see, because all this stuff can be kind of intimidating the first few times that you see it. But it's just a matter of kind of wrestling it down. All right. So I think that's good for today. We finished 2.6, or kind of our 2.6. So I'll adjust the functions part 1, and then we'll finish chapter 2, or kind of functions, next week, and we'll get into polynomials and rational expressions again, even though we saw them in chapter 1 already. Or kind of in the first chapter. So like I said, it's just going to be a lot of review of what we just did, spent a lot of time on in the first chapter, but yeah, pretty fun. I'm not seeing any questions. Are there any questions? Well, I'll stop the recording here.